Today we want to talk about what happens if I write sine as a function of x, right? So instead of talking about just sine of theta, we're going to talk about the equation y equals sine of x, where this is my x-axis, this is my y-axis, and I'm not graphing on the unit circle here. I'm graphing just like I would graph in the equation. So we're not in unit circle right now. So think about that x is your angle, y is the value that you get out of it, like 1/2, or 0, or -1. And so we're going to make an xy chart. We're going to pick kind of a lot of points here because I just want you to see what's happening, and go from there. See if we can figure this out. So I'm going to start with 0. And what is the sine of 0? Sine is y, so at 0, the value is 0, which means sine starts at the origin, 0, 0. We'll talk about this idea of key points in a minute. To me, key points are angles that give me really nice values for sine and cosine, right? Graphing square root of 2/2, or graphing radical 3/2, those aren't really that fun to graph, and so I don't usually graph those, but we're going to graph a little bit more on this first one just so you can kind of see how sine works when we graph it. So I'm going to go ahead and pick pi fourths on this first one. And what is the sine of pi fourths? Square root of 2/2, which I think is like 0.7071, because I'm a weird person to have that memorized. Roughly 0.7071. You can check me if you want. Square root of 3/2, I think, is like 0.866. I don't know why I know this. But to do this, which means not quite to 1. A good point is pi halves, right? Pi halves, those points on the x and the y axis of the unit circle, really nice points. What is the sine of pi halves? Point 0, 1, sine is y, means it's 1, right? We definitely going to have some graphing on the no calculator portion as well, that we got to know these values. And then here's what's really great. I'm going to write a lot of these out today, but here's what's really great. Once you get past the first quadrant, if we just keep picking multiples of pi fourths, am I going to keep getting the same numbers, only sometimes they're negative and sometimes they're positive? Which means if you know when it changes sign from negative to positive, you are going to be able to get a lot of values here without doing a lot of work. So if I kept going here to 3 pi fourths, 3 pi fourths is in quadrant 2, is sign positive or negative in quadrant 2? Y is positive, which means I know I'm also going to get 0.7071. And if I go all the way to pi, it's over here, what is the y value at pi? 0, right? Y, not x. Keep on going around, right? So, keeping the same distance apart, I'm going to go 5 pi fourths. If I'm at fourths, but now I'm down in quadrant 3, is sign positive or negative? Negative, so it's the same number. It's only now negative 0.7071. And then if I continue on down here, I'm going to get at 3 pi halves. And what's the sign of 3 pi halves? -1. And continue my journey back around at 7 pi fourths. I'm back to my 0.7071, so is it positive or negative in quadrant 4? Y is negative, so negative 0.7071. And I'm going to end back where I started, right? 0 and 2 pi are really the same point on the unit circle, which means I should get the same value that I got up here, right? Which is 0. And I'm going to stop at 2 pi right now, but we're going to graph more than that in a minute. But I would never need to pick any more values than 2 pi, because we know once I go around the circle once, those exact same values are just going to repeat, right? That's the idea of a periodic function, is it just keeps repeating itself over and over and over. So when we label our x-axis here, we're going to label angles. I'm not going to label all these. What I usually like to do is go to 2 pi. So let's not go all the way to 2 pi, so we can talk about what would happen next. Let's go a little bit before 2 pi. And you want to kind of be equally spaced, right? So like halfway in between that, we'll be halfway between 0 and 2 pi. Hi, great job. And then halfway between 0 and pi. I have. And then halfway between pi and 2 pi. 3 pi halves. And we actually picked the fourths too, which would be halfway in between that. But I'm not going to actually mark that. You can label them if you want when we graph them. What would happen if I labeled my x-axis going this way? What kind of values would I have over here? Yeah, same angles if I want to be equally spaced, but I'm going to be doing negative angles, right? So this is going to be negative 2 pi, negative pi, and halfway in between, negative 3 pi halves. Really important when we're graphing trig functions that you label your axis. Because if you don't label it and you just put tick marks, then I'm going to read it as 1, 2, 3, 4. And for trig functions, rarely should you have an x-axis behind them. They're going to be in What about my y-axis? Do I need to label lots of points on my y-axis? What's the biggest that it ever gets? What's the smallest it ever gets? -1, right? So you don't have to make a ton of points on your y-axis. And I actually want to make a decent graph, so I'm not going to make one way down here. I'm going to make mine one way up here. So you can see it. Roughly. Let's graph the nice points right now, and then we'll go back and talk about our 0.7071s. The nice points are the 1s and 0s, right? So like 1, 2, 3, 4, 5. Like usually you can get really 5 good points on a graph that you don't have to graph decimals. So if we graph those, 0, 0, and then at pi halves, it goes to its biggest value that sine ever gets, which is 1. And then if I jump to pi, it goes back to 0. Right? That's like quadrant 1 and quadrant 2. And then at 3 pi halves, it goes down to -1. And then I go back to where I started at 2 pi. I end at 0. And if you want to put the 0.701 in there, right? Like think about halfway in between here would be a little bit more than halfway, right? Like almost like 3/4 of the way. And it would be the same thing on this side. Right? So you can see this like smooth curve that we're making. The same thing happens in quadrant 3 and quadrant 4, except for we're at -0.7071. So if you went halfway in between those, they're going to be exactly at the same value, so it's going to make this kind of perfect little symmetric curve. And this is what sine, one period of sine looks like to complete all values. So I'm going to start here, and I'm going to go up. I'm going to go back to 0, and then I'm going to go down. And that one little curve there contains every value that sine ever gets between 0 and 2 pi. But the great thing is every value that sine ever gets, no matter what x is, that it just keeps repeating itself. And I don't know that you really want to make this keep going on your paper, but if I kept labeling this equally spaced, it just keeps repeating itself. So this side's just going to keep going up, and then going down, and then going up, and then going down, and then going up, and then going down, forever and ever and ever, in that exact same pattern, never getting above 1, never going below -1. So again, you don't have to do that, but that's one period of time. What I do want us to do is think about what's going to happen on the negative side. What's going to happen if I go to negative pi halves? Is it going to be the same value as pi halves? It's going to be opposite, because negative pi halves is going this way, right? So at negative pi halves, it's going to be at -1 instead of at +1. What about at negative pi? If I start here and I go to negative pi, what's the y value? It's still going to be at 0. What about at -3 pi halves? going to be plus 1. And then negative 2 pi is the same as positive 2 pi. Back to 0. Two ways you can think about this. One, if you know it continues this pattern over and over and over, up, down, you could say, well, if this side went up, I know if I continue the pattern back here, it has to go down and then back up again. So it's always just the exact same pattern. The other thing to remember about sine is an odd function. And the definition of an odd function is that it's the exact opposite on the other side of the y-axis, right? Symmetric with the origin, which means everything I got up here is now down here. Again, my things up. Odd function, some important things to know. The domain of this is all real numbers. Right, we wrote that out in 4-3, day 3. It's a nice smooth curve. You could pick anything you want. It goes on forever. You could pick 7 if you want. And what's 7 radians? Like, you have to think about it a little bit. The range of this is very restricted, right? I'm only going from negative 1 to 1, which is why sometimes on your calculator you get undefined number here, because you can't get values bigger than 1. So something to think about as we start to graph cosine. Are we going to get the same kinds of numbers for cosine that we got for sine? Are we going to get 1s and 0s and negative 1s and 0.7071? Those still exist for cosine, they just happen at different angles. So cosine is also going to look curvy like this, but it's just going to start in different places. And where sine is 1, cosine is not 1, right? So the angles are different, but they are going to look similar, which means I'm going to make a graph. So here's my key to how to pick what points, how to pick nice points. If you have the period, which for cosine, the period is just 2 pi, just like sine, unless we want to change it up. Here's the trick. Go from 0 until your period goes back, right? Which for us right now is 2 pi. But the period can change. We're going to talk about that too. But if it's from 0 to 2 pi, you just pick half of it. What's half of 2 pi? Pi. Great job again. What's half of pi? Pi halves. What's halfway between pi and 2 pi? 3 pi halves. It's really not an amazing trick that these are the points I pick. These are the points on the x and the y axis of the unit circle. They give me my lovely nice points. The book calls them key points. And I'm not even going to pick the pi force this time because we know now it's going to be a smooth curve. But now we're talking about cosine. So you have to make sure you give me the right value. Cosine is x. So at 0, what is the cosine value? 1, right? It's the point 1, 0. And cosine is x, sine is y. So cosine is going to start up at its highest value, where sine started at 0. And then what happens when I get up to pi halves? What is the x value at pi halves? 0, right? Because it's the point 0, 1. What about at pi? Negative 1. If it's negative 1, 0, 3 pi halves, back to 0, and at 2 pi, I should be back where I started, and back to the x being 1. And again, that completes one period of cosine because it goes through every possible value of cosine, and it ends back where it started. So if you stopped at negative 1, you haven't completed the full period because you have to get back to where you started. Okay, so I'm going to make this just like the last one, where I'm going to start with 2 pi. I'm going to break it in half, and if you find that that's really squished for you on the x-axis when you're labeling it, right? If you just put the next ones halfway in between and you didn't label them, I get that it's going by half there. You always want to make your axis evenly spaced, so never like make them uneven. And I'm going to do the same thing over here with my negative 2 pi. And just like sine, I only need 1 and negative 1 on my y-axis, so I don't want to take it negative 1. So watch what happens when I graph this. Again, we can put the pi portion there if you want 0.7, but 0, 1, and then it goes to 0, and then at pi it goes down to my negative 1, it goes back to 0 at 3 pi halves, and then at 2 pi I end up here at 1, which means if I'm making this a nice smooth curve, right, it should come down and come back up. Kind of really important. This is not going to keep going up, right? So notice I've kind of made mine where I know it's going to come back down, but it's never going to get bigger than 1. And again, just like sine, you can keep going here, and it's just going to keep going in that same pattern forever and ever and ever. So really important to me when you graph these on your test is don't ever make that like point up with an arrow, right? It should always be turning and going back down. Do you remember what we said about cosine? Was cosine even or was cosine odd? Cosine was the only even function. Which means if you remember that, cosine's great because an even function means it's the same on both sides of the y-axis. And if you forgot that, you could always just follow the pattern, right, that this has to go back down. Or you could actually just say, well, when I plug in negative pi halves, I'm still back to 0. And negative pi is exactly the same place as pi. And so I get this exact same curve without really having to do any work. I always think if I graph these two periods of cosine, it kind of looks like a W. We're going to spend a few days on this. It's really important that you kind of get the basic shape, the basic idea, because just like every graph we've ever done, we're not gonna just graph cosine, right? We're gonna graph transformations of cosine. And what if we stretch it? What if we shrink it? What if we change the period? So we got to get this down before we can do all of that stuff. Questions about this so far? I guess the domain is exactly the same as sine. The domain is all real numbers. The range is exactly the same, negative 1 to 1, which is why we always start that with this. Right, what is that? Oh look, I had a little sound here for you. Use key points to graph. Those are the nice numbers. So let's see. Oh, I got the notes. Y equals cosine x and y equals 2 cosine x. Maybe you can think about what's going to happen if we put a 2 in front of this. I'm going to graph cosine really quickly. We just did it, but I'm going to do it again, all right? I'm going to graph it kind of in the background. I'm going to do my 2 pi and my pi and halfway in between. And my negative 2 pi and my negative pi and halfway in between. My 1 and my negative 1. I'm not going to make the XY chart out again, but the big thing you got to think about is cosine starts at 1. At 0 radians, the cosine is 1. And then it goes to 0. And then at pi, it goes down to negative 1. Then at 3 pi halves, it goes back to 0 and then it goes back to 1. Those are my key points. Not pointy graphs, right? We don't want any sharp points on our sine and cosine. They're very smooth curves. Exactly the same thing on this side. So I just get to copy what I have over there and copy it over here. What I like to call the parent function, right? This is what we're going to base all of our transformations from there. What's going to happen to all those values if I multiply by a 2 in the front? Am I still going to pick my same values for x that I picked before? My period's still 2 pi. It's still going to just take me that long to complete the circle there. So I'm still going to pick 0 to 2 pi, and halfway in between there, and halfway in between there. What happens now, when I plug 0 in here, I'm going to get 2 times the cosine of 0. What's the cosine of 0? 1, but now I'm going to get 1 times 2, which means now I'm going to get 2. What happens when I plug pi halves in there? What's the cosine of pi halves? Still 0. But what's 0 times 2? Still 0. So that's not going to change. And maybe you kind of see what's going to happen and you don't need to make your chart, and that's okay with me. Our first one, still second chart. At pi, normally at pi, cosine is -1. But what's going to happen when I multiply by 2? It's now going to be -2. Oh. But at 3 pi halves, cosine is 0. 0 times 2 is still 0. But at 2 pi, normally it's 1, and 1 times 2 gives me 2. So if you think about what happens to normal graphs when we multiply a number at front, it stretches or shrinks it down. The same thing can happen for cosine, which means now I need another mark on my graph, right? So I have to go here and I need to mark another mark on my graph. Because this one's going to go all the way to 2. So the range -1 to 1 only applies for that parent graph. So the number multiplied in front is going to change it. So now this is going to start all the way up here. And then it's going to still go to 0. -2. Back to 0. Back up to 2. So I'm going to get that same curve, only stretching it by a factor of 2. So it should be twice as long. Think about what happens with x squared if you put a 2 in front of it. It's just stretched out. If you put a 1/2 in front of it, it's going to compress it down. It goes like this. And I'm just going to go on the other side now too. Right? You want to make this function for yourself. Show you that example before I give you all these words and these formulas, because if you just think about the number in front, that's going to affect our range. For sine, trig functions, we have special words for them. Instead of saying that that's a structure or string, I call those the numbers. I don't know. So I'm giving you the whole big ugly thing right now. All the transformations we can do represent A, B, C, and D right now, right? We just did an example with an A value. We're going to talk about what B does to that today as well, but C and D we're not going to talk about yet, but we'll get there eventually. So A is the scale factor for us. Well, we know that's a structure. Where's the word that we use for this? Sorry, didn't have to. This is hopefully not new ideas to you. This is true for every single function we've ever graphed in our life. that if A is bigger than 1, it stretches your graph. If A is less than 1, it's shrink or compression. Your range will always be decided by what A is. So you can say that the range of sine and cosine, I just use sine here, will always be just negative A to A. That's why if A is 1, negative A to A. We call this the amplitude of the graph. And the amplitude is just whatever A is. The book definition always is kind of confusing, but it's half the distance between the maximum and the minimum value. So think about, normally for sine, the maximum is 1 and the minimum is negative 1. So that's a distance of 2, so half of 2 is 1. So that way, but the last one we did, our maximum was 2, and our minimum was negative 2. That's a distance of 4. Half of 4 is 2, right? So that's half the distance between the maximum and the minimum. So you're going to see questions today that say state the amplitude. The amplitude is just the absolute value of it. Because the negative does something different to it, right? What does the negative do to our graph? Yeah, it's a reflection, right? So if there was a negative in front of your graph, right? And again, I'm using sine, but it also works for cosine. If there's a negative, that means that it's reflected in the x-axis. Think about x squared. If it's negative x squared, it opens down instead of opening up. And then we've talked about this idea of the period of the function. How long does it take to complete one portion of that graph? Normally it's 2 pi, but if there's a number multiplied by x, right, we call that the b value, then it changes the period. It changes how long it takes for me to get all those values. So our formula for period is 2 pi divided by b. Again, if b is 1, that's why our period is 2 pi. But if b is some other number other than 1, it changes our period. It changes our key values as well. All right? So the period is how long it takes to complete one cycle of the graph. So for sine, this is what you have to have in your head. One cycle of sine is like 1 hump up, 1 hump down. So quadrant 1 and quadrant 2 are my positive values, quadrant 3 and quadrant 4 are my negative values. Normally it's 2 pi, but if b is something else, then it changes it. And for cosine, one period is starting up on your y-axis, going down to your lowest value, and ending back where you started. That's kind of the big idea of what shapes our sine and cosine. What time do we get out of here? 6 minutes. So, I wanted to look at one with a period change here, just to kind of show you how would I change my graph if my period was different. And so step 1 is figuring out what b is, right? So my period is 2 pi over b. What is b in this problem? b is 1/2, right? b is not 2. If it's like 1/2 x. So my period here would be 2 pi over 1/2. And what is 2 pi divided by 1/2? Dividing by 2 is the same, divided by 1/2 is the same as multiplying by 2, right? You just flip it up, it's 4 pi. Which means that this graph, to get that shape of sine, you're going to have to go to 4 pi instead of 2 pi. And so this is what I mean by your key values. You should have 5 key points that you want every time. And here's how you're going to do it. You're going to find your period, and every single time you're going to start at 0, you're going to end at your period, which in this case is 4 pi. And then you're going to take half of it. What's half of 4 pi? 2 pi. Great job. What's half of 2 pi? 1 pi. And what's in between 2 pi and 4 pi? Halfway. 3 pi. You see how these numbers have changed? Those will change when your period changes. Next time you're saying your period, I've said a lot of times. What's great is if you pick these 5 points, these values should always be the zeros, the ones, and the negative ones, which is amazing because, and you can actually work it out if you want. If I plug 0 in there, 0 divided by 2 is still 0. What's the sign of 0? Still 0. See what I mean by you have to know these values? So this is where you got to be careful. I'm not asking you what the sign of pi is. I'm saying we're going to plug pi into this function. So I'm going to plug pi in there, and that gives me pi halves. What's the sign of pi halves? 1. See how these are the same values we got when our period was 2 pi? Which means if I plug 2 pi in there, 2 pi divided by 2 is really just the sign of pi, which gets me back to 0. So guess what's going to come next? Or maybe we're not there yet. If I plug 3 pi in there, 3 pi over 2, what's the sign of 3 pi over 2? Like we need to have some trig quizzes here of knowing this. -1. And if I plug 4 pi in there, what's 4 pi divided by 2? 2 pi. And what's the sign of 2 pi? Back to 0. If you look back at the chart that we made for just sine of x, it was these exact same key values, key points, but different x values. So, I'm holding you hostage. I'm going to go 4 pi, 2 pi, 3 pi, and pi. And this means when the period is 4 pi, we're going to take a lot longer to reach that same shape, but we should still end up with our positive values and our negative values. So I'm going to just graph 0, 0. At pi now, it goes up to 1. At 2 pi, it goes back to 0. At 3 pi, it goes to 1. -1, sorry. And at 4 pi, it goes back to 0. So you see how that's that same shape? It's just stretched out over a longer period. You don't have to graph the original sign in there if you don't want to, but I want to really quick just to show you what regular sign would look like. It still starts at 0, but at pi halves, it would go up to 1. At pi, it would go to 0. 3 pi halves, it would go to -1, right? So this is normal sine, right? 1 hump up, 1 hump down. This is sine with a period of 4 pi. Oh. So you see how we could fit regular sine in there twice? Over because the period is 2 pi. Okay? So I don't really have time to do the last one, but just to kind of look at it, it's my favorite one. Read the directions on your homework today. You don't have to graph all of them. Some of them just say, what is the amplitude, what is the period? Amplitude is the number that stretches it vertically. What will be the amplitude of this graph? 5, the number in front. The period is not just 2, right? You have to remember this. The period is 2 pi over b. What is b in this problem? Give this number. So the period is just pi. And I want you to look in the back of the book of how they describe this. Like, how would I describe this? This graph is stretched by a factor of 5. Or you could say the range is now 5 to -5. And the period is pi. Which means this one is going to take less time to complete that full cycle than if the period was longer, it would take more time to get there. So try the homework. I'm not going to be here tomorrow, but I'm going to leave a video. I'm actually going to leave some videos of my also kind of going over graphing this for you. Okay?
volunteers to help us, please? I need Daniel Boren, Josh Parker,